Okay, now we get to the last of the succession of these videos on the Hipparchus scale, and we're going to title this Calculating Distance Using Absolute and Apparent Visual Magnitude. The equation that we just developed was that the apparent visual magnitude was negative 2.5 log of absolute luminosity over absolute luminosity of the sun, 1 squared distance of the sun, the distance of a star in light years squared times the AU conversion. What I'm going to do is now separate these two. I'm going to use the property of logs. Log of AB is equal to log of A plus log of B. Right? So I'm going to take this portion and then this portion and separate them. Negative 2.5 log of absolute luminosity over absolute luminosity of sun. And then minus 2.5 log of, well, 1 squared is just 1, so we don't really need that. Distance squared, 63,239.6717 squared. Right? What is this? Well, remember, the absolute magnitude was what? Negative 2.5 log of absolute luminosity over absolute luminosity of the sun plus 4.83. Remember that one from the first video? So you have this 4.83. So this part, negative 2.5 log of absolute luminosity over this one, we can substitute. We can say this one is equal to mv minus 4.83. Negative 2.5 log of this, right? We could take the 4.83 and bring it here. So this one will be mv is equal to big MV minus 4.83 minus, and then this one, I'm going to separate it further. Log of 1 over d squared minus 2.5 log of this one. 1 over 63,239.6717 squared. So there's lots of stuff going on here, right? Now we're going to further simplify this, and it's going to be a real beautiful looking equation. MV is equal to MV minus 4.83. And then this one, what I could do is just take the to the top. Remember, log of 1 over x to the nth power is going to be log of x to the negative n, right? And then this negative n comes negative n log of x, right? So it's good to know a lot of properties of logs in order to analyze this. So this one is going to be d to the negative 2. Negative 2 is going to come out and it's just going to be multiplied times this, which is going to make it positive 5, right? So positive 5 log of just d, right? The distance d of the star from us. Then same thing is going to happen to this. The negative 2 is going to come out and it's going to make it positive 5 log of 63,000. Okay? So 63,239.6717. Okay? And on top of that, let's not forget, there is that 0.74, 26.74. So we need to add that here, negative 26.74, because that's your base reference. That's the apparent visual magnitude of the sun. So you have negative 4.83 comes from the absolute visual magnitude of the sun when we substituted this one, right? And then the 26.74 comes from the apparent visual magnitude of the sun. So now what do? We take this one and this one. These are just variables. Okay? This one is a number. This one is just a number. This one is just a number. Let's calculate what that's equal to. Right? Negative 7.565. Okay? So just lots of numbers. But where are we headed with this? Now we can take this, subtract it here. Okay? We have here MV minus MV. Take this 7.5 positive 7.565 is equal to 5 log of d, right? Take the 5, divide it into this, 5, and you get here mv minus mv over 5 plus, what is this? Now what am I left with? By combining all of these logs, by rearranging things, what was my goal and what did I end up with? Well, what I ended up with was an isolated equation where it would relate the distance of a star in light years to the apparent visual magnitude of the star and the absolute visual magnitude of the star, right? If I know its apparent visual magnitude already, and if I know the absolute visual magnitude, I can calculate the distance. If I know the apparent visual magnitude and I know the distance, I can calculate the absolute visual magnitude. And if I know the absolute and the distance, I can calculate the apparent. So if I know any two of these three, I can calculate the other one, right? So let's circle this one. But we're going to even develop this one step further. What I'm going to do is this distance, instead of writing it as light years, I'm going to want to write it in parsecs. 1 parsec is equal to what? 3.26. So to be exact, it's 3.26163626 light years. So if I want to rewrite this so that the distance is written in parsecs, okay, what do? I say I multiply this d times 3.26163626, right? So now I can express this d as 1 parsec, and if I multiply it by this, it will convert to light years, right? Because remember, this equation applied when the distance was expressed in light years. So if I want to express this now in parsecs, I put d and I multiply it by the conversion. What that will do is that this one, log of d plus log of this one. So I have to go mv minus mv over 5 plus 1.513 is equal to log of d plus log of this number. Okay, so let's see what log of that number is. Interesting thing is going to happen. So this number ended up to be 0.513. So log of d plus 0.153. When that number comes over here, look what's going to happen. Amazing, amazing, amazing. You have mv minus big MV over 5. 1.513 minus 0.153, you just get 1. That's equal to log of d. Now what could I do? I can raise both sides to the power 10. Because I have a perfect one here. Look what's going to happen. 10 to this power. 10 is going to cancel this, and I have d is equal to 10. I can separate this. b is equal to 10 to the a times 10 to the b, right? If you multiply this, you can just add the power. So I'm going to separate this part and that part. I'm going to have 10 to the mv minus big MV over 5 times 10 to the 1. It's just going to be 10. Okay? So what's the final equation that I'm left with? I have the distance to a star in parsecs is equal to 10 times 10 mv minus mv over 5. Okay, so what does this mean? So the equation with all those big numbers, 63,000 and everything, all the conversions and everything, the equation came out to be a nice, simple looking equation, right? So let's say the apparent visual magnitude of a star, mv, is equal to, what are some typical apparent visual magnitudes? Okay, in reality, we have, let's say 2. Let's say the star Polaris, for example, whose apparent visual magnitude is 2. Let's say its absolute visual magnitude was also 2. Okay? So this is Polaris. If its absolute visual magnitude was 2, what would that mean? Remember, the sun gets a 4.83. So this Polaris would be 2. That means the Polaris would be brighter than the sun, right? This way. So it would be, remember every 2.5 is 10 times brighter. So it would be a little more than 10 times brighter than the sun, okay, if Polaris was a 2. And we already said its apparent visual magnitude is a 2, so that we already know, right? If this was true, what would the distance of Polaris be from us? Distance in parsecs, it would be 10 times 10. When these are the same, 2 minus 2 over 5, what do you get? 0, right? 10 to the 0 is what? 1. That means Polaris would be 10 parsecs away from us. Okay? Now you can convert to light years. Each parsec is 3.26 light years. So that's 32.6 light years away. If Polaris's absolute visual magnitude was 2, and we know its apparent visual magnitude is already a 2, then Polaris would be 10 parsecs away. But this doesn't just apply to Polaris being 2 and 2. Any star, right? If you have a star, apparent visual magnitude 6, absolute visual magnitude 6, 6 minus 6, 0 is 10 parsecs away. So now you know why all of this was set up that way. Why was the sun's apparent magnitude negative 26.7? Why was the sun's absolute visual magnitude 4.83? At that time, they just looked like numbers. And we had no way of seeing, okay, why? Where's this 4.83? Why is the negative 26.7? Where are those reference numbers coming from? It was all intended so that when you do all of the math, all of the logarithms, all of the conversions, what you end up with is an equation, a simple looking equation, such that if the absolute visual magnitude and the apparent visual magnitude of a star are the same, that star is 10 parsecs away from us, which means 32.6 light years away from us. Now we can find out the distance to any other star, okay? So now, let's say a star's absolute visual magnitude is -5, that means it's much brighter than the sun, okay? And let's say its apparent visual magnitude is +4, that means it doesn't look too dim, right? So you have to visualize on the number line each one. MV, little mv. Try to visualize so you can see what's going on. If a star's MV is -5 and the sun is a 4.83, that means that star is a lot brighter than the sun, right? If the apparent visual magnitude is +4 and the sun is all the way negative, right? And we know that Polaris is a +2 and Sirius is -1.4, right? That means that star is dim looking. You might be able to see it in the desert on a good dark night, right? So how far away would that star be? And then you can say D 10 times 10, MV is 4 minus -5 over 5. Okay, what is that going to be? 30 parsecs away. Okay, so if the star is absolute -5, +4, it's 630 parsecs. From there you can convert to light years by multiplying by 3.26, and you get about 2,000 light years away, right? Let's say the absolute visual magnitude was -5, apparent visual magnitude +9. That means it looks dimmer. Same absolute, but it appears dimmer. So it goes over here, +9. What do we expect? If it's the same brightness and it appears dimmer, it's got to be farther away, right? So you put over here, you put MV 9. You're going to have 6,309 parsecs. Okay? So the star is 10 times farther away, right? So you can practice any combination of the apparent visual magnitude and any combination of the absolute visual magnitude. So once we determine how bright the star is, using some techniques and analysis and observations, once we determine how bright it appears to us, the apparent visual magnitude, we can use this equation to find the distance to that star. So now it became a nice and compact, workable, usable equation. Okay? So this finishes the series of the Hipparchus scale, absolute and apparent visual magnitudes, and its connection to distances to stars. Thank you very much.